The most important thing with the PRV is that it is your last line of defense. It needs to be sized correctly. If it's too small, it won't protect the system. If it's too large, as we discussed earlier, you get chattering and issues. So there are many standards, again, depending on your local province, country, area. What I'm focusing on here is EN 13126, which is a European and British standard, which we use constantly here. Again, even though there are many different forms of standards throughout the world, you'll find that if you comply with something like a recognized standard like 13136, it tends to be acceptable in most places, or it can be easily modified to the needs of another standard, for example, North America. So 13136, it looks at three scenarios that you size your valve based on it. External heat source, which is effectively a fire, by far the most common one that everyone thinks about when they're sizing a PRV. Internal heat, which I don't see used a lot, that tends to be the scenario where you would maybe have a heater coil or something inside your system, and you're worrying about that running out of control and adding heat that way, excessive heat that way. And compressor flow being the other one. So again, typically for transcritical CO2 systems, we sometimes see valves located on the discharge line, and they'll be sized to cope with the flow rate of the compressor. So if there's some blockage further down the system, the valve will open and allow the total flow rate of the compressor to be discharged. And the standard then says that you should consider as many of these as are applicable, and you should obviously use the worst case for what valve to pick. So there's some calculations involved, which we'll dive into in a sec. They require system properties, refrigerant properties, and PRV properties, obviously, as well. And basically, you're looking at two terms. You're calculating a required flow rate, the QMD, as it's called. This is what's required to keep the system safe in these scenarios. And you're then calculating QM, which is the actual rated flow rate of the valve. And effectively, you're making sure that you make sure the valve has more rated flow than your requirement.